Welcome. Can you hear me? Yes, now you can hear me. Thank you. So welcome, everyone, to our session on the AP1000 reactor. My name is Julie Gorgevans, or Julie Gorgevans, as you prefer. I work on our new build opportunities for the European region. And so, at Westinghouse, we truly believe that the nuclear energy has a significant role to play to deliver carbon-free, sustainable, reliable energy systems to the world. And obviously, renewables is a very important part of that system, but it is our mission to design energy solutions that can work with renewables in delivering the values and the targets of many countries and customers. So I do have first a short video that explains that vision. Okay, so sorry, because there was supposed to be sound, but that didn't work. But so that basically was the summary of what I wanted to discuss today. So now here we go for the long version and the more animated and vocal version. The first thing I'd like to do is summarize what is the AP1000 reactor, what was the journey that we embarked on at Westinghouse when we developed the advanced passive technology, and some of the key characteristics of the resulting product. After that, I would like to touch upon operational performance. We now have had some operational units, AP1000 in units, for a few years. So obviously, we start seeing the results of what we've tried to achieve, both in terms of online performance and outage performance. And finally, I'll touch upon what we are doing to prepare for future projects and what are our prospects, particularly in this region. So AP1000. If there is one word to remember of everything I will say today, it's simple. People often believe that we want it to be passive, but what we wanted was to be simple. And we want it to be simple and at the same time safer. When we started working on the advanced passive technology, it was in the 80s. We started with AP600, then we moved to AP1000, the bigger version. But it was really from noticing the trends in the industry. We had been building pressurized water reactors for decades already, from shipping port all the way to the 80s. Building them in the United States, building them in Europe, partnership, licensing our designs in different countries, in Europe, in Asia. And what we were noticing is that as an industry, we always strive to be safer. And that's obviously, that mission doesn't change. It's still our mission today. But the way we were achieving this was by adding more complexity to the plant. We also want it to be more reliable. Obviously, we want a customer to produce power. But we were also doing this by adding more components, adding more layer of equipment. And an increased level of complexity in the plant design was resulting in plants that were longer to build, more expensive to build, more risky to build. And so we took a step back and we tried to think about what can we do to break that paradigm that the more performant the plant is in terms of safety, in terms of reliability, the more complexity we need. And this is how we made some of the key design choices in AP1000, which is, for example, going to passive safety. Why is simplification so important? Again, because it's easier and less expensive to build, but also to operate, to maintain, and even to decommission if you think about the whole life cycle of the plant. The better equipment is the one you don't need in your plant. That's really the philosophy. So if we look at what does an AP1000 look like, it doesn't look that different from an other pressurized water reactor. We still have a reactor pressure vessel, a pressurizer, steam generators, reactor coolant pumps. But for each part of the plant, whether safety or whether something that supports normal operation, it's always striving to say, what can I simplify? What can I improve? And this is driving really some key design choices. And one of the most emblematic design choices in AP1000 is, of course, the choice of reactor coolant pump technology. It wasn't always easy, but why did we make that choice? If you look at what you have in a traditional pressurized water reactor, you have very good pumps. They perform well, no problem. But they come with a very complex network of support systems. And not only do you need those support systems for normal operation, you also need them in case of an emergency. And so through the years, we even added backup to the safety systems to ensure they will be there, which is good. It's a safe solution. Nothing wrong with that. But it is very complex, lots of equipment, which means lots of equipment to purchase, install, and obviously buildings to build to house them. So in AP1000, the question was, how can we simplify this? How can we simplify the support systems and the pump design? And so we looked at what technologies were available. And one of them was actually used in previous generation of plants, was also used in other applications who had very similar requirements to us. High reliability. Obviously, if your RCPs don't work, you don't produce power. So it's very important that they are reliable. We also want them to work for extended periods of times. And obviously, they are inside containment, not in the most welcoming environment. And so we looked at what was available. We identified this. We looked at the possibility to upscale the design to fit our requirements in terms of flow rate. And this is how we chose it. The beauty of it, much more simple support systems. Even better, no support systems in case of an emergency. The only support system you require is when they are operating. So that was kind of what happens for the normal operation systems. But obviously, what we are known for is the passive safety systems. So passive safety systems, they're really beautiful. They're elegant. They're simple. This is why they have lots of advantages. The first one is that they require very little to be actuated. During normal operation, when you don't need them, they're basically on standby, and you only need one valve per system to change position for them to be actuated. After that, they're just going to continue operating because they only are based on the laws of physics. Gravity isn't going to disappear, so they will continue operating. And that for more than 3 days. And only then, with very simple operator actions, can you further extend the operations of the passive safety systems. That was great. That was always great. But the benefit of this simplification, obviously, was further highlighted after the events at Fukushima. Not only do we not rely on external power, we also don't rely on the on-site diesels, but we actually also don't rely on the on-site batteries for station blackout. When we were designing AP1000, one of the first things we did was looking at what are the major sources of risk in an existing unit. And in an active plant, one of the most significant contributor to the core damage frequency is actually the loss of offsite power event. So first thing we did is like, okay, so what can we do? Well, you can do one thing. As I said, passive safety systems, they only require a one-time valve alignment in order to actuate. Well, we can make that one-time alignment without power, because we basically made the system so that they do need power to maintain the valve in the non-actuation position, so that if we lose all power outside, the valve will automatically switch to the open or closed position, depending on the system, letting the passive safety systems actuate it. Another benefit of the passive safety systems is how compact they are. They're very simple, but they also have a very small footprint. They have a very small footprint because they all have almost no support systems. So you can put them all inside containment. And inside containment is the most protected area that you have in your plant. It's protected by the thick containment vessel, and it's further protected by the robust shield building, which is around. So all those very simplified design, very few support systems. Actually, in some cases, we don't need any support systems at all, because if we lose them, they automatically actuate. And self-protected by the shield building made this a very, very robust and unique in its response plant for Fukushima-like event and extreme events. Okay. So I mentioned how the passive safety systems were very compact, very small footprint. But actually, we applied the simplification to everything in our plant, even on normal operation systems. This resulted in an overall reduction of footprint, which is quite unique. If we compare AP1000 against many different designs, and we bring it back to a megawatt electrical basis, we are very small. Why is that important? Well, in a nuclear power plant, you have one reactor pressure vessel, but you have kilometers and kilometers of cables, pipework, ductwork, and all this is only based on how big of a building do you have. So by reducing the footprint of the unit, you reduce the amount of field work that you need to install all those small things that are actually the majority of your unit. So those are a lot of driving a significant reduction both in field work and construction duration. So I mentioned before, nuclear energy, yes, it has a role in the future energy mix, but it has to integrate. And it has to integrate with renewables, and that means that one of the key characteristics that our design needs to have is load follow capabilities. And so this is not something we often highlight about our design. But actually, if you compare to others, you will see we have an extraordinary range of power that we can achieve. We can go as low as 15% for stable operation, 15% power for stable operation, all the way to 100%, of course. And then we can accept REMs, pretty rapid changes. And this is thanks to a few things. The first one is we use gray rods. So what does it mean is that we did not accommodate those load changes by chemical shim. We use mechanical shim. It's fast acting. What we do also is have very large margin to safety limits. So we have a very large operational range which allow us to absorb the change. And we have a digital INC, which is very performant and help us smooth the response on the core point of view to adapt to the core load. And finally, another simplification on AP1000 is if you look at our reactor coolant system, if you look at our power level, at the volume we have in the RCS, we actually have a very large pressurizer. And this was done so that we would have a significant operating band so that we can absorb all the temperature changes during load follow without having to release also from the reactor coolant system. So not only does it respond well, does it perform well on an operational point of view, but it also reduces the amount of waste we generate as we do load follow. We have other additional operational features. Our standard fuel cycle is 18 months, but we can operate at 24, and we're designed for 24. We have a 93% capacity factor, which is actually being exceeded by the operational units, so we are very happy. We are capable of 17-day refueling outages. Obviously, our operating units, which are in the first cycles and first outages, are not there yet, but you will see that they are getting very close. And also, one thing that we did, addressing the lessons learned of the operating fleet, was looking at critical states that needs to be beefed up, that had to be reinforced in terms of reliability. And mid-loop operation is one of those aspects to which we had put particular considerations. So we have units operating in China. They've been performing excellently. That started with startup and commissioning, where things went extremely quick, extremely well. Further demonstrating our passive safety systems through the startup test program. The first operating cycles also went very well. They also did load follow, so they already tested the full operational range that AP1000 can offer. And as I was saying, in terms of refueling cycles, refueling outages, sorry, the first refueling outages, the quickest of the 4 was in 28 days. The others were not far. But that's an extraordinary performance for the first outage in a new technology. And for the second outage, considering that the first outage is a lot of one-kind type of maintenance to observe that everything is OK. A second refueling outages, as you see, they're getting very close to the 17 days that I was mentioning. Something which is also not very known, but at the Haiyang AP1000 site, they actually are part of a larger infrastructure project where they also provide district heating to the local area as well as fresh water. And they will continue developing that infrastructure complex to include a desalinization plant very soon. So I already mentioned our units in China, 2 at Sanmen, 2 at Haiyang. And then we obviously have 2 units under construction, very close to completion at Vogel in Georgia, United States. The last thoughts that I would like to share today is really about how we're preparing for the future projects. So I mentioned before, our objective was always to be simple. But another objective of AP1000 was always to be standard as much as possible. And what we mean by standard is maintaining the nuclear island design the same. The same in China, the same in the US, the same wherever we're going to go. And the main reason for this is obviously so that we can share lessons learned. We can share experience. So after delivering the China units, actually already in between the China units, we can take the learning from the first one to the next ones. Once we were completed in China, we could take whatever lessons we had and bring them to Vogel. After Vogel, we are ready to bring even more lessons into the future projects we will deliver. And those lessons, they're not just into what are we delivering, so what the design looks like, but how we are delivering. And I think if other vendors are in the attendance, that we will all share this. There is a lot to learn about how you deliver a project, both in terms of how you deal with your supply chain, how you select them, how you interface with them to exchange information, and so on. And so we do have a number of prospects in this region. We are committed to working in Europe with all our customers and all the countries in order to help them achieve their goals. And it's not just with AP1000, it's with the whole range of products and services that Westinghouse has. Obviously, you may have heard that we recently signed an agreement with Ukraine for AP1000 reactors at Khmelnytsky. We are currently doing a front-end engineering and design study for Poland. We are very excited to see a new nuclear nation entering the nuclear world. But it also goes beyond this, as I said. I know it's written on the Czech Republic, and it's not Czech Republic, but we also signed a VVR 1000 fuel licensing contract, for example, for Kozloduy in Bulgaria, because we also want to open the supply chain for customers that may need it in order to make them more independent or the incumbent suppliers. And I think this is the end of my presentation. Thank you.